my screen. So, welcome to the discussion of the fifth theoretical exercise in compiler construction. So today it's all about crazy, stupid x86-64 assembler, which, carries a more than 40-year legacy, and you feel it every day. As you can imagine, I'm not a big fan of x86 assembler. But anyways, so that's the platform we're going to use this year because everyone has probably an x86 machine at home. And so I thought we'd, create a couple of questions which might be interesting also in the context of code generation later on. So first I gave you this bit of a convoluted set of assembler code, which makes up the assembly implementation of a function foo as it could be generated by a compiler. And well, for those of you who are not really accustomed to reading assembly or disassembly, let's just give a quick overview of what you see here. So this is the base address of that function here, which is just 0 because we haven't linked that function yet. This would be relocated later on. Nevertheless, we don't need it to understand the code. So on the left-hand side here, these numbers are actually the addresses in memory, so the offsets from that base address, where this specific assembler instruction here on the right-hand side is stored. So for example, this first move instruction here, moving ESI to EAX, takes 2 bytes. The opcode and parameter bytes would be the 2 bytes here, and they would be stored at addresses 0 and 1. And then the next instruction starts at address 2. So this is again a 2-byte instruction, this test instruction, and so on and so forth. One thing you might see is that we have stuff like relative offsets here. So this jump if less than or equal instruction here jumps to a target address of 15. So down here. But this 15 is not encoded. Oh no, it is encoded actually here. So it's 0f. Okay. So that's actually here the absolute offset. That might be patched later on. So the first part of the question, and what you see here, one thing to mention is that on x86, instructions can have different lengths. So there can be 1-byte instructions here, like our red queue instruction at address 15, which is just the byte C3. We have lots of 2-byte instructions. We have some 3-byte instructions. But in the worst case, x86 instructions can be up to 17 bytes long. So this makes it quite a bit harder to disassemble the code and to really find code if you're doing something like forensics, trying to figure out what's going on in your assembler code when you don't have any source code. And that's exactly what we're trying to do here. So we have this assembler code function, which might have fallen out of our disassembler. And the first question is, does this function actually take parameters? And if so, how many does it take? So for 64-bit x86, values to functions are passed in registers as long as we have enough registers. So if it's less than or equal to 6 registers, 6 values, we pass them in these 6 registers. So DI, SI, DX, CX, 8 and 9. So this is this crazy x86 register numbering, and they're passed in exactly that order here. So the first parameter of your function is passed in DI, the second in SI, and so on. And depending on the size of your parameters, so if it's a 64-bit value, it would be RDI, so the indication for 64 bits of the DI register, or if it's a 32-bit value, for example, a regular integer, it would be the E, the extended DI registers, EDI, and so on. And how can you figure out that a function actually uses a parameter? Well, a good indication is actually that a register value is used without being initialized first. Now, that might also be an uninitialized variable, but let's assume that our code is just doing reasonably well. So this means we have a move instruction moving the contents of the ESI to the EAX register here, and also testing the ESI register here without changing it first. So ESI is used. So that would be the second parameter here. Then we see that further down here, EDX is tested without overwriting it first. So that would be the third parameter. And finally, the first parameter is, for example, used down here in this add instruction to add the value of EDI. So just reading it. to the EIX register here. So we don't see any RCX register used here. So this would mean our function either only has 3 parameters, or it would have a 4th parameter, which is never used. That could also be the case, but let's just assume the most common case. So this has 3 parameters here. We have no ideas what these parameters are named because, well, essentially without looking at additional debugging or symbol information. So just from a disassembly, the information about variable names, for example, is lost, and they're only mapped to registers or memory addresses, which then your assembly code uses. So next question was, does the code of the function include an if statement, and how did you find this out? So here you would have had to figure out what these bit strange looking instructions on address 2 and address 6, so test ESI, and test EDX mean. Now I've copied it from well, some description of the instruction set. So the test instruction performs a bitwise AND on 2 operands. Well, if I do an operand AND of itself, it doesn't change the result, right? And we don't care because the result is actually thrown away. What's interesting is the meta information. So what this result was. And according to the result, the ALU in your CPU sets a certain number of flags. And especially important are the 0 flag. So it indicates if the result of that bitwise AND was the value 0. So if you do a bitwise AND of a variable with itself or of a register with itself, the only way to actually get a 0 is if that register was a 0 in the beginning. So test can test for zeros, and it also sets the sign flag. So the sign flag assumes that the result would be a 2's complement number. So in a 2's complement number, you know that the most significant bit, so bit 31, for example, for a 32-bit integer, would indicate the sign. So if it's a 1, then it's a negative number. And if it's a 0, then it's a positive number or 0. So what we do here is we test ESI against itself, so our second parameter that we passed here. And if this is LE, so this is a conditional jump here, less or equal to 0. So equal is exactly the value of the 0 flag. So if the 0 flag is set, then this E actually matches. And L means less, so less than 0. So that would mean the sign flag would be set. So this instruction does a conditional jump if either the sign flag or the 0 flag is set, or in other terms, if the value of ESI, which we tested here, is less than or equal to 0 when we interpret it as a 2's complement number. And our second test does something similar for the EDX register, so for our third parameter here. And this only tests for 0 or not 0. So if the value of our third parameter in EDX is 0, we just jump down here to address 16. So we have an if instruction here. We actually have 2 if instructions here. So the first one here, and this jumps to address 15. So it immediately returns if our second parameter is less or equal to 0. And we have a real if, so we're either executing the code starting at address A or the code starting at address 16 here, depending on the fact if EDX is not 0 or if it is 0. Okay, so hooray, we found ifs. So actually one is just a simple if here, and the other one executes code either if the condition is fulfilled or not. So this would be usually compiled from an if then else construct. So the next question was to find out if this function includes a loop, and of course how you found this out. So we usually find loops because there's a relative conditional jump that's going backwards here. So it jumps to an address that is lower than the address of the conditional jump address itself. And so we have 2 of these cases here. Here we use a compare between 2 registers, for example, between DX and AX. And if DX is greater than AX, we jump to address C, so 3 or 4 instructions up. And we have a very similar construct here, actually exactly the identical construct, just with a different target address. So if EDX, the value in EDX is greater than EAX, we jump to address 16 here. So what we cannot find out is, was this actually a while loop, a do loop, a for loop, or just somebody actually manually coding goto in C, which is still allowed, but discouraged, obviously, because our compiler can actually decide to transform this. And if you remember our intermediate code transformations, we've seen that we only, for example, need to implement while loops, and all the other forms of the loops, like a for loop and a do loop, can be implemented in terms of a while loop. And since our compiler does this exactly in the intermediate representation, in our code that's generated later on in this machine code, we actually cannot distinguish these anymore. But it doesn't really matter, because you can write a loop in any of these forms and it would result in the same machine code being generated. So the final question was maybe a more difficult one than you thought. Does this function return a value? And the correct answer is maybe. So if you look at the application binary interface for Linux, so the System 5 ABI for x86-64, it not only gives you the information in which registers the parameters of a function have to be passed, but also that the result of a function has to be passed in the AX register, so EAX, for example, for a 32-bit value in our case. And since the value of EAX is modified here by adding stuff to it, we can assume that we're returning it, especially since in our first instruction here, we're moving ESI to EAX and then testing ESI. So here, when we return at address 15, we'd have some value in EAX already that can be returned. We don't know this for certain. We can only be sure about this if we can have a look at the code calling the function to see if this value is actually used. Otherwise, it could also just be an artifact of the compiler that uses RAX for something, and if this return value is not used by the calling function, well, then that's simply what happens, which means that the AX contains a value, but it's never used afterwards, so it's probably overwritten very soon. All right, so that was a piece of ugly assembler code, and we have more pieces of ugly assembler code. But first, maybe to try some sort of decompilation. So what would the corresponding C code look like? It doesn't make much sense, to be honest. So we know it's a function foo because our disassembler got this symbol information, at least that it's foo, but the name doesn't really matter. And we've seen it uses 3 parameters. We've just called them A, B, C. So A is stored in EDI, B is stored in ESI, and C is stored in EDX. And we assumed it would return a value, so we give it int as a return type. And then we can actually try to translate these machine instructions back to C. So the first one, well, let's just ignore this because it's just moving data around. So here we test the ESI register. So we test our variable B, which is in ESI. And if this is less or equal to 0, then we jump to 15, and 15 just returns the return, contains the return instruction. So if B is less or equal to 0, we just return. And what we return, if we return something is B, because we copied the value of B to our return value register EAX before. So if this value function returns a value, it would return B here. Well, otherwise, we'll fall through to the instruction at address 6. So here we test for EDX equal to 0. And if it's equal to 0, we jump to 16. Otherwise, we just fall through here. So if it's equal to 0, so I've switched this around. If it's not equal to 0, we have this code here because we're just falling through. And if it's equal to 0, we have that code here. So let's first take a look at the code up here. So this XOR of EDX with itself is also a nasty shortcut because it's quicker than actually moving a value 0 into a register. So XOR of EDX with itself just means do an XOR of the register bits in EDX with itself. So you know XOR, whenever there's 2 zeros, it produces a 0. Whenever there's 1 in the bit position in each of the parameters, it also produces a 0. And since we XOR one value with itself, both situations in which a 1-bit could occur after the XOR never can show up, because that would mean that the register would be different to itself. So this is the trick here. XOR of a register with itself just zeros the register. And it's faster than actually moving a constant 0 to that register, because the instruction is shorter. And that's actually instructions compilers use to generate more efficient code. So we know EDX was actually our variable C here. So we set C to 0 here. And then we have a loop here. Where does this loop come from? So let's see. We have a couple of instructions, 2 adds, and then we have a compare and a jump if greater to address C. So up here. So this would mean that we fall into our loop after the XOR. We start our loop without checking anything at the beginning. Then we do the first addition. So we add EDI to EAX, and we know the value of B was copied to EAX up here. So we add EDI, so our variable A, to variable B. So B equals B plus A is the first instruction of our loop body. Then we add the constant 1 to EDX. EDX is our variable C, so we increment C here. And then we check if the value of EDX, so we compare the value of EDX with EAX, and if EDX is greater than EAX, so if C is greater than B, then we jump up. So while this condition is fulfilled, we jump back to the beginning of our loop. And since our loop starts at address C, that's where our loop body starts here. So that's our loop here. And the other loop is the code down here. So this doesn't initialize C, but it immediately subtracts A from B. Then it adds 1 to our variable C. And then we have a comparison again, which is the same as above. So if C is larger than B, we jump back to the beginning of our loop. So we have a do while loop, and we do this while as long as C is larger than B. Well, and then finally, we would return something here, and we would assume that B is returned. This function doesn't make much sense. I freely admit this, but any more real-world complex function would probably have been too much confusing. And so actually there are automatic tools trying to do this. So decompilers. So there's, for example, EDA Pro, which is a commercial disassembler decompiler reverse engineering tool. There's a free version for x86-64 out. And I think the most recent update, I'm not sure if it's out yet or the next couple of weeks, they include a decompiler. And there's also a free tool, which was, that sounds a bit scary, designed by the NSA. This is called GIDRA, G-H-I-D-R-A. And this is also a reverse engineering and decompilation tool. So these tools can actually, do something which, I used to call it, well, this reverse engineering is something which you can compare to hamburgers. What's this? So essentially, there's an easy process. Going from C code to assembler would be you have a cow and you want to make a hamburger. I hope there's no vegetarians out there who would hate me now. Going from assembler back to C code is the other way around. So you have a hamburger and you try to reconstruct your cow. As you can assume, that's a bit more difficult. But that's exactly what these decompilation tools and reverse engineering tools try to achieve. So they get this, well, exactly the hex codes. So they're disassembling these. So these assignments are mostly unique. So there's a problem that you need to figure out where an instruction starts, because instructions have different lengths. And then they detect some patterns like these jumps here, forward and backward, to figure out a C code that is a bit easier to read than the original assembler code. Actually, I haven't tried putting that assembler code through a decompiler. I should probably do this. So disassembling was also the next task, or actually decompiling. So we gave you a bit more of a simple assembly code function here. And what you should see in this example, that actually there's not one unique mapping from C code to machine code, but there can be different C code variants that result in exactly the same machine code. So you were asked for this piece of assembly code here on the right-hand side to give some equivalent valid C code. So this is a function f, well, and this moves a value of a, so that might be a global variable here, extern unsigned, global variables a and b. So it copies the memory location where a is stored, the contents to eax, and the contents of memory location b to edx. Then it does a logical AND operation to a long word, so to a 32-bit value, and it does an AND with the constant 255. So that's the right-hand side here. EDX contains B, so it does an AND of B and 255. The result is again stored in EDX, so now we subtract EDX from EAX. So EAX is our A, so we subtract B and 255, which was the intermediate result, from our variable A. And then we finally copy this back into memory because it's a global variable at the location where A is stored, and then we return from it. So that would be our first version of the C code, A minus equal B and 255, or A equals A minus B and 255, which would be the same. So the next question, or next part of the question, was giving different versions of C code that could compile to the same code. And one of these should have a different function signature than the one described already. So for example, you could do a modulo here instead of an AND operation. So B integer modulo 256 would be exactly the same. And then you could say you negate this value and add it to A. Well, maybe you need to think about this for a second, but this is exactly the same. Or you could rewrite it as hex numbers here. So you could say A equals A minus B modulo hexadecimal 0x100. It doesn't really matter because the bit pattern representation, obviously, of 0x100 and 256 is obviously the same in regular 2 complements numbers. We could also have something like this here on the lower left. So we do a typecast to unsigned character. Now, typecast to unsigned character from an integer means we're only interested in the character value that's stored in B, so in the least significant 8 bits. And since this is unsigned, we don't do a sign expansion. So if we do this conversion here, this actually sets the most significant 24 bits of B to 0 and just keeps the least significant 8 bits. And that's exactly, of course, what's happening here with this AND operation. And then you subtract this. So that could also be an additional option. Or you could do something crazy like this, like just add a third parameter that's never used here, and a number of additional parameters which you never use. So your code, if it's optimized, would still look the same. So it's just the same as a function on the left-hand side, just having some stupid additional parameters, and maybe this time returning a character pointer. On a 32-bit machine, at least, this would be the same. So that's actually not, that's a bug. Yeah, so that's not 64-bit code here on the right-hand side, because then a pointer would have to be 64-bit. So that would probably have been just a remnant of the 32-bit code I tried. All right, so with these pointers here, it's a bit more complicated. So the final task, and I think that's also useful, or that would be useful if we had more complex data types in our VSL language for which we want to generate machine code, was to actually figure out what some machine instructions actually mean. And these mnemonics here for the machine instructions are sometimes a bit difficult to read. So for example, the first one was move ZBL from AL to EAX. So move ZBL is a move instruction, obviously. And it fetches a byte from a register or from memory. In this case, of course, from a register, not from memory. And then it does a 0 extend. So B means it fetches a byte. Z means it does a 0 extend. So when we store it in something that's bigger than a byte, all the other bits that don't fit in a byte are set to 0. And then we say, and we want to store it in a long value. So we do something like this. So that would be an unsigned character, for example, because we're reading a byte, so just 8 bits, and we store it in a register which has 32 bits, and we set the other 24 bits to 0, so that might be an unsigned character, or a uint8 underline t would also be an option. So there's always multiple options. The second one here uses the offset addressing from a base pointer here. So we're addressing a variable at memory location -28 plus the value in our base pointer register here. And this is a move L. So move L moves a long word, so a 32-bit word. And this is copied into EDX. So this can be an int or an unsigned int value. So it's not a difference. So if you just move it, you just move the whole 32-bit, and it doesn't matter how this is interpreted. So you don't have any signs for move instructions because it just copies bits over. And this is moving usually from the stack into the EDX because we're referencing memory relative to our base pointer, and our base pointer, as we've seen, is a register that is the pointer to the beginning of our local stack frame. Now, number 3 is move SBL, and then also something relative to our base pointer into EAX. So move B, we've already seen it just moves a byte. Now this S means it's signed, so Z means 0 extent. S means it's a signed value. And that what this does is it looks at the most significant bit of that byte that we're loading, that is at address -32 of RBP. And if this bit is 1, so if this would be a negative 2's complement 8-bit number, then it copies this bit to all the other bits in that 32-bit value, so to bits 8 to 31. So with a move S instruction, we always do the sign extent. So we copy bit 7 from that byte, if we do a move SB, over to bit 8 to 31. So this means if we take a look at that value as a 2's complement number, it would still be the correct 2's complement number in this 32-bit form. Whereas when we extend do just a 0 extension, as in the first instruction here, then if it was originally a 2's complement number, as a 32-bit number, it would no longer be a negative number, for example. So that's the difference here. And yeah, that requires thinking about number formats, stuff like that. So your compiler can be quite a bit more simple, but in real-world compilers, you'd have to do stuff like that. Then our fourth instruction uses a move L, so we're moving a 32-bit value again. And now we have this complex addressing mode. So we're having RDX as the register storing a base address, for example, the base of an array in memory. And RAX is the index, so maybe the array index. And then we have a multiplier here. So this indicates that we're multiplying the index by 4 and then adding this to the value of the base address, to the DX register. So this means, for example, if we have a value of RAX equals to 3, we would multiply it by 4, so we get 12. So we would address RDX plus 12. And so with an index increment of 1, we get an address increment of 4 here. And so this means we would address, well, sections of 4 bytes each, which of course fits to our move L because move L expects to move 4 bytes. So this would be maybe an array of ints or unsigned ints, as again, we don't see any difference in the move instruction here. And so the offset in RAX is first multiplied by the size of that integer or unsigned integer, so 4 here, and then it's added to the base address here in RDX. So that's the usual way to implement register accesses in x86 assembler. And that's very convenient because you only have to generate one instruction for such an array element access here instead of doing several on some RISC architectures. And the final one is the one down here. So again, we have a move ZBL. So we know it's a byte read, it's 0 extended, and it's stored into a long word. And this has, again, a relative addressing. So it takes the offset of 4 added to the address in RAX. So it's RAX plus 4, which is the address here. And that might be the 4th or actually 5th character, of course, in the string, because we're starting to count from 0. So RAX might be a character pointer here. And we're addressing the character at index 4, so the 5th character in our string. We're moving it to EAX, so that's a 0 extended byte load. So EAX contains the 8 bits at this address RAX plus 4 and 24 0 bits and the most significant bits. And then we do a move SBL of the AL register into EAX again, which would actually then do a sign extension. So this is a bit of a convoluted instruction just to produce some knots in your brain. So this would actually do the byte extension of the unsigned byte we just loaded. So this would be a character instead of an unsigned character here, because we're doing this sign extension explicitly here. And yes, that's stupid. And the obvious question, no, this won't be on the exam. So that was just, to tease you a bit, to get you accustomed to reading and figuring out x86 instructions, because you need to do a bit of this when you generate code. But it's easier since you don't have to figure out what instructions are doing. You just have to figure out for each of your intermediate representation instructions in your tree, for example, what code is needed. And we've seen loops, we've seen ifs, we've seen functions. And that's essentially what you have to use here. And that's actually all for today. So I'll stop recording now.